For our final unit of the semester, we're going to talk about rotational motion. So to start out, we'll talk about equilibrium. And a concept that's important for equilibrium when we're talking about rotation is torque. So let's take a look at this pile of rocks. How do the rocks remain balanced? So these rocks are in equilibrium, and this is the kind of equilibrium that we call static equilibrium. Right, so we're familiar with this from translational motion, the type of motion we've been talking about all semester, where an object moves from place to place. Right, you can have an object have zero acceleration while sitting still, but you can also have an object moving that has zero acceleration, right, as long as it's moving at a constant velocity. So for rotational motion, we can have static equilibrium, like this pile of rocks that is not rotating at all. But we can also have dynamic equilibrium, like this wheel that is rotating, but it's rotating at a constant rate. Okay, so what are the conditions to make an object be in equilibrium? So you might say, well, to be in equilibrium, you have to have all the forces balanced. Right, and that's the first equilibrium condition. So if we look at this hockey stick, we can see that there are two forces pushing on it. So you could imagine, this hockey stick has been dropped onto the ice, and two opposing players run into it, and so they have forces that point in opposite directions. So, or maybe it's two people trying to grab this stick, and they're both pushing in opposite directions. So we see the free body diagram there. The forces balance out, so the net force is zero. Right, so we would have constant velocity. If the stick were initially at rest, it would stay at rest. If it were initially sliding in some direction, it would keep sliding in that direction at the same velocity as long as the forces are balanced. But is that enough? Here we take those same two forces and just move them away from the center of mass. So now we can see that the arrows there that are kind of purplish in color, they indicate that the hockey stick is going to rotate. But our free body diagram still shows the same picture, right? We have a force to the left and a force to the right. They balance each other out. So if the forces are offset, it's going to start the object into rotation. So it wasn't initially rotating and it starts rotating. That's not equilibrium. Right, so it's not enough to just say the forces are balanced. We also have to worry about where those forces are applied on the object. So now we can't just do our free body diagrams and treat all of our objects as if they're just a simple point. We have to acknowledge the fact that objects are extended objects and can rotate. So torque is a concept that sort of takes force and moves it into the realm of rotational motion. So torque accounts for both the force that's applied to an object and the distance from the pivot point. Now, the pivot point usually is going to be given. So if we look at this picture of a door, we know that the door is going to pivot around the hinge, right, if it's going to rotate at all. So here we have our definition for torque. So torque is the lowercase Greek letter tau. And I've written it here as the force perpendicular times r. Now this is a little bit different from the way that you'll see in the flipping physics video, which I'm also going to share on Blackboard. And it's also a little bit different from the way it's pictured on the diagram, right? There, the perpendicular subscript is put on r. So what does that mean? Well, it means that not only does the force applied and the distance from the pivot matter, but it also matters what angle between r, which is called the moment arm or the lever arm, and the force vector happens to be, right? So I often like to, we're used to breaking down forces into their components, and so that's why I like to use the perpendicular component of the force, right? So in this picture, the force appears to be exactly perpendicular to the moment arm, which means it's perpendicular to the door itself. So that perpendicular component can be found by taking that force times the sine of the angle between the force and the moment arm or the lever arm. So if we want to think about how all these things combine, right, we have to worry about the force, the distance from the pivot point, and the angle. We have a really intuitive understanding of this based on understanding how we open a door. And again, you can see the flipping physics video on Blackboard for a good video illustration of this. So how would you open a door? What's the best way, most efficient way to open a door? Where would you apply this force? Well, first of all, we know that the bigger force that you apply, the bigger torque's going to be. Okay, so that part's simple. So if you're going to try to open a door, would you apply the force close to the hinge or far from the hinge? And would you apply it perpendicular to the door or parallel to the door? So you'd apply the force far from the hinge, right? So the doorknob is not just near the far edge of the door to make the latching easier, but it's also a good place to apply the torque, and you're going to push perpendicular to the door, right? So if you push parallel to the door, you'd just be pushing the door right into the hinges, and you get no torque at all. That's no way to make a door rotate. So, and you know, especially if you have a heavy door, if you tried to push it real close to the hinges, you might get it to rotate eventually, but it's going to be a lot more difficult than if you push near the doorknob at the far, make your moment arm as large as possible. And of course, perpendicular and parallel aren't the only options, but they're the sort of two extremes, right? So if you are perpendicular to the door, you can think you're not wasting any of your force, right? You're pushing it all in the way that's going to maximize the torque. But if you push parallel, you're wasting it all, right? You're not doing anything to open the door. And if you're at some other angle, you're somewhere in between. Now, the other thing that's important to note is that torque is a vector, right? So the direction is going to matter. So not only the magnitude, but the direction. So in this class, we're mostly going to be able to break that down into whether the torque would cause a clockwise rotation or a counterclockwise rotation. Now that's a little bit ambiguous because if somebody were looking at the door from the opposite perspective, they would disagree on which direction is clockwise or counterclockwise. But you can solve that by just having a diagram to refer to. So you have to pick one of those directions to be positive, right? Either clockwise or counterclockwise is going to be the positive direction. And generally in math, we take the counterclockwise direction to be positive. So you can see here in this diagram, there's two. You'd have the same torque in the two pictures in terms of magnitude, but because the force has flipped direction, it's going to change the direction that the door would rotate, right? So in the picture that's on the left side, you get a counterclockwise rotation, which is a positive torque, and in the other picture, you get a clockwise rotation, which is a negative torque. So now that we have this idea of torque, we can bring in to our definition of equilibrium. We can say our second equilibrium condition is not only do you have to have the forces balanced, but you need to have the torques balanced. Right, so here we have a picture of this concept in action. We have these two children who look like they were in an airline safety manual previously, but now they're playing on a seesaw or a teeter-totter or whatever you want to call it. I think a lot of these have been removed from parks because they're basically death traps. But they're still good for physics, right? So we have a pivot in the middle, right? And that's where the object's going to rotate around if it's going to rotate at all. And there's going to be some force from that pivot, right? But if we look at the calculation that's below the picture, we can say the torque from the pivot, well, that's whatever that force is, times the distance from the pivot point. But the distance from the pivot point is 0. So any force that goes through the pivot point is not going to be able to rotate the object. Right, so that force is important to balance out the downward forces of gravity from the children, right, for the first equilibrium condition, but it's not going to play into calculating the torque. Now, if we look at the torque from the child in the blue overalls, there is, the force points down, and the moment arm is horizontal, right? And it's that distance from where the child is sitting to the pivot point. So we can multiply those two together, and you can see that I haven't included an angle. Well, that's because they are perpendicular to each other, right? So I'm looking for the perpendicular component of the force of gravity in this case. But that would be the entire force in this case, because the force is perpendicular to the moment arm. The other way that you can think of that is just say, well, the sine of 90 degrees, if you wrote down the whole calculation, the sine of 90 degrees is equal to 1. So we can see that if it was just that child on the teeter-totter or the seesaw, it would start to rotate in the counterclockwise direction, so that torque is going to be positive. And the torque that is caused by the child in the pink dress is going to be negative, right? So we need that total torque to be 0 to make to meet the second equilibrium condition. So because one's positive and one's negative, we know that in principle that's possible, but they have different masses, and so there's going to be different forces. So if we have that situation, right, so let's say that the child on the right is more massive, what can we say about where they need to be positioned in order to make the torques balance out? Right, so what can we say about the moment arms? So should the bigger child sit farther from the pivot than the small child? Should the bigger child sit closer to the pivot? Do they need to be equidistant from the pivot, or does their positioning not matter? So hopefully you saw that the bigger child should sit closer to the pivot point, right? So we have a bigger force, and so therefore if you multiply it by a smaller moment arm, then we can balance out the two torques. So as an example calculation, let's say child 1 has a mass of 20 kilograms and is sitting 2 meters from the pivot point. If child 2 has a mass of 30 kilograms, how far should they sit from the pivot point? So we know that the two torques need to add up to 0. And we already know that torque 1 is going to be given a positive value and torque 2 is going to be given a negative value to stay consistent with our definitions. So they can add up to 0. So we take the force in each case, which is just going to be the mass of the object times g, force of gravity, times the lever arm, and the appropriate sign. Right, we don't have to worry about any angles here because the forces are perpendicular to the moment arms. So we get this expression here. So we can see that g is going to cancel out, and with a little algebraic rearrangement, we can solve that for R2. So we can see that the units work out, and we will get a distance of 1.3 meters. So if the child sat farther away, it would start rotating. So if the heavier child sat farther away, it would start rotating in the clockwise direction. Now, as we'll look at in later examples, if you have a net torque that's unbalanced, it's going to cause an angular acceleration. And for angular acceleration, we call that alpha. So here is a weird grown man who's at the playground deciding to push a merry-go-round with no children on it. I won't try to psychoanalyze him too much, but he's applying a force that is perpendicular to the moment arm, right? And he's away from the center of, or the axis of rotation. So there's going to be a torque from him, and if we assume that there's no friction, then that's going to be the only torque, so it's not balanced. Right, so not only is the merry-go-round going to start rotating, but if he keeps applying that force, it's going to rotate faster and faster. So here's another example where we have both unbalanced force and an unbalanced torque. So we have the hockey player that scoops up the stick, tosses it to his teammate. Right, so he needs to apply a force to it that's greater than the force of gravity to get it to accelerate upward. And then because he doesn't apply that force at the center of mass, it also makes the stick start rotating. Now, once he stops applying that force, the only force acting on that stick is gravity. Right, so that's going to be an unbalanced force, so it's going to start accelerating downward, which we see. Right, the stick after he throws it up, and then it's in free fall. And it's also going to be in rotational equilibrium at that point, right? Because gravity acts at the center of mass, and the stick is rotating around its center of mass. So the rotation stays constant as it flies through the air. Right, we can make what we'll call an extended free body diagram here, where you actually kind of draw a picture of the object and draw the force vectors at the place where they're actually applied. So we can see that the force of gravity, I've tried to find where the center of mass would be on that stick. The force of gravity points down. Because we know that he's able to lift and launch the stick upward, we can say that the force of the stick is bigger than the force of gravity. But it's also going to cause rotation around the center of mass, because that force is, there's some moment arm, right? There's some distance between the force of the stick and the center of mass.
Okay, so I've got this big metal stick or pole that I found in my garage. It's kind of heavy. If I put my hand right at the center of mass, then I can exert with one hand the force that's going to balance the force of gravity. And because the force of gravity acts on the center of mass and my hand is acting in the center of mass, there's no torque on the stick. Now, if I want to, I'm getting a little tired here, so if I get my other hand involved and I balance, spread them out evenly around the center of mass, then I can hold it with my palms up, and I've got about half the weight in each of my hands. And because my hands are, this hand on its own, the right hand, would exert a torque that way, and the left hand would exert a torque the other way, but because they're equidistant from the center of mass, their torques are also going to balance out. Now, maybe you've had this experience trying to carry a heavy piece of furniture with someone. Right? If you end up being real close to the center of mass and the other person's far away, right now I can feel that my left hand is supporting a lot more weight than my right hand. And that's because they're still adding up to the total weight of the stick, but because of the torque, to balance out, this hand has to exert a lot less force, right? So you wouldn't want to carry something like this with a friend. Now, things get really difficult if I move it so that the center of mass is not in between my hands anymore, right? And I can't even really do it with my palms up. It's pretty heavy. But if I turn this hand over, if I need to hold it near the end, now it's a lot harder to do than it was when I had my hands near the center of mass. Why is that? Well, I still need to provide a total force that is enough to balance out the force of gravity, but my left hand now has to push down, right, to try and equal out the torque. So because my left hand is pushing down, my right hand has to have an upward force that balances out the weight of the rod, plus it also has to compensate for the downward force of my left hand. So this really, I can't do it for very long because of that extra force that's needed. So, if you want to carry something efficiently, you'd want to carry it near the center of mass. But if you're like a pole vaulter who really needs to use that whole length, well, then you got to put your hands like this, and it's just going to feel a lot heavier because you have to compensate for that torque. It's a lot heavier than the one that I used.
So here's an extended free body diagram for that example video that I just showed, and this guy here is supposed to be a kind of sad-looking pole vaulter, as I mentioned in the video. So if he's holding the pole with his hands equidistant from the center of mass, then his right hand and his left hand can apply equal forces and therefore equal torques that are going to, well, equal in magnitude but opposite in sign. So the pole won't rotate. So they just need to add up together to balance out the force of gravity. Now, if he shifts a little bit, the free body diagram still looks the same. We can see that the force from the right hand needs to be bigger because it's got a smaller moment arm. It's closer to the center of gravity. And the left hand force isn't as big, right? So this is like if you're trying to move a couch and you're lifting it near the center of mass, but your friend's on the end, you're going to have to supply a much bigger force than they are. And then finally, if you're far out from the center of gravity, now in this case, if you let go with the right hand, you'd actually probably see the pole rotate around, rather than rotating around the center of mass, it's going to rotate around where the left hand is. So now the force of gravity is causing a torque, right? So the right hand needs to push down with a force that's even bigger than the force of gravity, right? Because it's closer to the pivot point, which is now the point where the left hand is. So the right hand has to push down with a force that's bigger than the force of gravity on the pole to balance out the torque. But then the left hand needs to supply an upward force that's more than twice the weight of the pole, right? Because it needs to not only balance out the force of gravity, but it needs to balance out the force from the right hand, right? So that's why you always want to try and lift something heavy near the center of gravity, so that you don't have to compensate for these torques and end up exerting a much bigger force than you otherwise would.